This paper proposes a novel trajectory prediction approach, RAFLTP, which leverages graph neural networks to address the challenges of secure data sharing in autonomous driving applications. The authors introduce an asynchronous federated learning strategy based on reputation evaluation, where vehicle reputation is quantified through interactions between vehicles. Data providers release data structures under differential privacy constraints to ensure security while reducing redundant data. The approach utilizes deep reinforcement learning, specifically proximal policy optimization, PPO, to group vehicle trajectory models based on reputation values, minimizing the federated learning cost. The authors highlight the limitations of traditional federated learning approaches, including the lack of complete trust in multiple parties, uncertainty in participant data quality, and extensive prediction delays. To address these challenges, the proposed approach employs a reputation-driven asynchronous Florida scheme, complemented by a reputation-enhanced PPO algorithm. The approach also introduces differential privacy techniques to enhance the privacy and security of shared trajectory graph models and vehicle reputation values. The paper provides a comprehensive review of related work in trajectory prediction, including data-driven approaches, deep learning methods, and graph-based models. The authors discuss the importance of trust management systems in vehicular networks and the limitations of centralized and distributed trust systems. They also highlight the potential of blockchain technology in enhancing resource sharing under 5G conditions. The proposed approach is evaluated on two large-scale vehicle trajectory datasets, NGSIM and ApolloScape, with different real-world scenarios. The results demonstrate that the approach effectively ensures data security, enhances trajectory prediction accuracy, and adapts well to various traffic scenarios. Comprehensive ablation studies confirm the effectiveness of the method components. The paper contributes to the development of a novel trajectory prediction approach that addresses the challenges of secure data sharing in autonomous driving applications. The proposed approach has the potential to enhance the accuracy and reliability of trajectory prediction, while ensuring the security and privacy of shared data. The proposed asynchronous federated learning (FL) model for trajectory prediction addresses the inefficiency and poor security of current methods. In a distributed data sharing scenario, multiple participants with their own data collaborate to realize a joint task while protecting sensitive information. The system model integrates a permissioned blockchain module and an Florida module, where the blockchain handles data retrieval and sharing transactions without recording raw data. Each participant has a local dataset containing historical trajectory data, and the goal is to predict future positions of all observations. The proposed architecture employs a graph-based approach for model training and data sharing, where vehicles undergo authentication to become legitimate nodes in the permissioned blockchain. Participating vehicles compute reputation values based on original data quality, which are recorded as shared transactions and in local models. The super nodes collect weighted graph models perturbed with differential privacy noise from vehicles and group them based on reputation evaluation using the PPO algorithm. The high-quality vehicle clusters receive priority in deep aggregation. The global model is trained through asynchronous Florida and broadcast to all committee nodes, which drive the consensus process for the permissioned blockchain. The reputation-based hybrid blockchain for data sharing involves collaborative learning of a federated graph neural network model across decentralized parties. Object trajectories are transformed into weighted graphs for interaction modeling, and graph convolutional networks handle spatial interactions and temporal convolution captures time-based features. The weights of nodes are determined based on the similarity of trajectories between vehicles. Differential privacy is incorporated to safeguard data privacy, where instead of sharing local vehicle model parameters, the shared graph neural network model is used to retrieve and compare confidence levels, filtering out graphs with high trustworthiness and low similarity. This prevents model parameters from leaking vehicle trajectory information and improves the efficiency of the next global aggregation. The proposed approach ensures secure and efficient data sharing while preserving data privacy. The paper discusses a novel approach to data sharing among vehicles in an IoT network, leveraging blockchain technology and a reputation-aware data sharing mechanism. It proposes a method for vehicles to share data securely and efficiently while maintaining privacy and ensuring the relevance of shared data. The authors introduce a reputation value derived from trajectory similarity among vehicles, which enhances data relevance and improves the quality, accuracy, and reliability of shared data. The reputation value is calculated using the similarity between two trajectory segments of vehicles, considering velocity, position, and orientation differences. Local opinions for subjective logic are used to describe the reputation between two vehicles, taking into account both positive and negative events and the quality of communication. The authors also suggest combining local opinions with suggested opinions from neighboring vehicles to form a common opinion. This common opinion is then combined with the local opinion to form the final opinion, avoiding potential spoofing. The final reputation value is calculated, incorporating the final opinion parameters. A consensus mechanism, proof of reputation, POR, is proposed to enhance node computational resources and lower communication overhead. Committee members are chosen based on their reputation scores, and they oversee the consensus process and acquire knowledge of the data model of the requested data. The paper concludes by discussing the importance of prediction accuracy in evaluating the performance of trained local models during the consensus process. Here is a combined summary of pages 7 and 8 of the research paper. The paper proposes a reputation-driven PPO vehicle clustering algorithm to optimize asynchronous federated learning for trajectory prediction in Internet of Vehicles, IOV. The algorithm utilizes a reputation evaluation mechanism to group nodes with high reputation values, enabling the asynchronous training of trusted vehicle clusters. The reputation mechanism is designed to solve the problem of insufficient heterogeneous model aggregation and significant global model update delays in federated learning. The proposed approach involves a reputation-based PPO vehicle clustering algorithm, which prioritizes the deep aggregation of high reputation vehicles, leading to a superior global aggregation model. The algorithm is designed to minimize execution time and enhance model accuracy by precisely categorizing vehicle nodes according to their reputation values. The reputation of learning, ROL, is introduced to describe the high or low reputation value of a vehicle in the aggregation process. The ROL is calculated based on the characteristics of the data, including the local learning time cost and communication cost of each vehicle. The total cost of federated learning in time slot t is given by the equation quart_f equals quart_r plus quart_e, where quart_r represents the reputation-based cost and quart_e represents the execution time cost. The PPO-based node clustering algorithm is formulated as a combinatorial optimization problem, which is solved using a Markov decision process. The algorithm updates the system policy with a value function, and the optimal resolution for vehicle reputation categorization is ascertained using PPO. The reward function is customized to add 1 to the reward value for choosing high reputation vehicles, ensuring that the algorithm prioritizes the aggregation of high-quality data. The proposed approach enables effective interpretable federated learning for trajectory prediction, preventing data redundancy and ensuring the elimination of vehicles with high similarity in the set of neighboring nodes. The algorithm is designed to adapt to dynamic traffic conditions and optimize local prediction models, leading to improved model accuracy and reduced execution time. The proposed methodology, RAFLTP, utilizes a reputation-based proximal policy optimization (PPO) module to dynamically aggregate data from high-quality vehicle data providers. The PPO algorithm is employed to determine the optimal value of lambda that maximizes reputation accumulation, as shown in equation 23. The reward function R, street, lambda t, assesses the standing of taking action lambda t at time interval t, and the overall cumulative reward is presented in equation 22. The experiments are conducted on two renowned datasets, NGSIM and Apollo Scape Trajectory Dataset, with the basic information listed in Table I. The study area includes two road segment datasets, US 101 and I-80, and the Apollo Scape Trajectory dataset was gathered in an urban area during rush hour. The evaluation metrics used are root mean square error, RMSE, average displacement error, AID, and final displacement error, FDE. The ablation study demonstrates the advantage of the proposed approach by conducting experiments on the Apollo-Scape trajectory dataset. The results show that the basic encoder-decoder network exhibits the highest error, primarily due to its limited consideration of vehicle interactions. However, with the incorporation of grip-based model enhancements under the proposed method, the aid shows a substantial reduction. The impact of the differential privacy module is also apparent, as it enforces constraints to filter out abnormal and redundant data, resulting in more robust and secure model aggregation. The influence of deep reinforcement learning (DRL) methods is compared, and the results show that the PPO algorithm is more stable and adaptable to changes in both datasets, converging quickly after positive feedback. The training time of the PPO algorithm is also found to be 34.5% faster than that of the DQN algorithm. Additionally, the influence of bad nodes on different modules within the overall framework is analyzed, and the results show that an increase in the number of bad nodes significantly degrades performance. The paper presents a novel approach to enhancing the security and robustness of vehicle trajectory prediction in a distributed learning framework. It introduces a differential privacy module that protects against data breaches by adding noise to the data structures shared by vehicles. This noise effectively limits the impact of anomalous data nodes and redundant nodes on prediction accuracy. The authors also propose a reputation quantization mechanism, which uses reinforcement learning to group vehicles according to their reputation scores, thereby improving prediction accuracy. The authors conducted several experiments to evaluate the effectiveness of their proposed solution. They found that a higher number of bad nodes results in a lower average displacement error, AID, which can be attributed to the reinforcement learning-based grouping of vehicles according to their reputation scores. They also observed that higher local and global aggregation frequencies lead to faster convergence and improved prediction accuracy. Similarly, higher invocation frequencies of the differential privacy module also lead to improved prediction accuracy. In terms of the impact of differential privacy hyperparameters on prediction accuracy, the authors found that a privacy budget of epsilon equals 0.3 strikes a good balance between data privacy and utility in the Apollo-Scape dataset. However, in the NGSIM dataset, maintaining a balance between privacy budget and utility requires epsilon equals 0.4. The authors also compared their model with 7 baseline methods consisting of state-of-the-art trajectory prediction methods. While their solution did not achieve state-of-the-art results, they managed to reduce the AID by 11.2% and the FDE by 10.2% on the Apollo-Scape dataset compared to the GRIP method, surpassing even the spectral result. The paper presents a novel framework for distributed trajectory prediction in autonomous driving, leveraging graph neural network tools and asynchronous federated learning-based data sharing. It introduces an interpretable reputation quantization mechanism to ensure data security and privacy. The proposed method, RAFLTP, uses a spectral clustering algorithm to group vehicles based on their reputation levels, optimizing the efficiency of federated learning aggregation. Experimental results show that RAFLTP is more tolerant of bad nodes, enhances the security of distributed trajectory prediction tasks, and significantly improves prediction accuracy. The paper also discusses the integration of RAFLTP with 6G networks and further enhancing efficiency in future research. In the experimental section, the authors compare the performance of RAFLTP with other state-of-the-art methods using 2 datasets, Apollo-Scape and NGSIM. RAFLTP outperforms other methods in terms of average displacement error, AID, and final displacement error, FDE. The paper also includes a visualization of prediction results using NGSIM datasets, showing that RAFLTP's predictions closely match the actual trajectories. The computation time of RAFLTP is reported, which, although higher than GRIP++, remains acceptable compared to other methods. The conclusion summarizes the contributions of the paper, highlighting the innovative framework for distributed trajectory prediction, the use of graph neural network tools, and the asynchronous federated learning-based data sharing approach with an interpretable reputation quantization mechanism. The paper discusses the application of deep learning techniques in vehicle trajectory prediction, focusing on dynamic graph and interaction-aware convolutional networks, DGI-net, as well as trajectory prediction in dense and heterogeneous traffic using weighted interactions, traffic. It also references proximal policy optimization with prioritized trajectory replay, PTR-PPO. DGI-net, proposed by an et al., is a neural network model that leverages both spatial and temporal information to predict vehicle trajectories. This model utilizes dynamic graphs to represent the interactions between vehicles and their environment, which significantly improves prediction accuracy. Traffic, introduced by Chandra et al., addresses the challenge of trajectory prediction in dense and mixed traffic scenarios. This approach uses weighted interactions to model the influence of different types of vehicles on each other's movements, enhancing the reliability of predictions in complex traffic conditions. PTR-PPO, developed by Weiliang et al., is an optimization algorithm designed for reinforcement learning tasks, particularly those involving trajectory planning and control. By prioritizing the replay of trajectories with high learning potential, PTR-PPO aims to accelerate the learning process and improve the performance of reinforcement learning agents. These research papers collectively highlight the advancements in vehicle trajectory prediction and reinforcement learning, demonstrating the potential of deep learning techniques in enhancing safety, efficiency, and autonomous driving capabilities in various traffic scenarios.